Valkenburg. He's with Evonik, and he's going to talk about troubleshooting post-ISCO performance using geochemical data.
Thanks, John. I have to agree with you. It's time passes quickly. Anyway, let's see here. We'll figure this out. Thanks, everyone, for being here. Hopefully, you find this interesting. I'm going to go at my number of slides per minute is going to be a little slower because it's less pictures and just a little busier slides. So anyway, introduction here. What can we learn from geochemistry? Of course, how we directly measure persulfate and some of its degradation byproducts and what they are. Obviously, we give you some clues in the little image to the right, like you couldn't figure that out. And then we'll try and show you a little bit about what we see when we have what we consider to be a successful application. If we have an application that's a little less successful, is that like rebound, is it recontamination, or is it some kind of a poor distribution issue? And by looking at the geochemistry, you can start to sort that out. It's really especially important with pilot tests because sometimes people misattribute their results because it's like, well, I didn't get what I expected. So common challenges, of course, we want to establish contact, but how do we do that? Do we have preferential pathways? What are their application strategies? Like, you know, for instance, if you can do soil mixing, well, you're going to obviously get good contact, but a lot of times we do injection because it can be much more efficient. And then we think about our injection volumes, target ROI, what our porosity is, how we're getting things distributed. And of course, different reagents have different properties. In talking about ISCO and being with Evonik now, it was Adventus, Adventus, FMC, PeroxyChem, and now Evonik. I've been doing the same job for 16 years, and I'm on my fourth company. John and I worked together back in the Adventus days, but anyway. We're working with persulfates because that's what we make, and sodium persulfate and potassium persulfate have very different solubilities, which ties into where they're best used. Of course, we got to consider flux and residence time. Definitely been on sites, and I'm sure you guys have too, where sometimes you do an injection and everything washes away a lot faster than you think. And then, of course, sorbed and non-target demand is like how much mass is sorbed onto the soil, how much oxidant will it take, what's the soil oxidant demand of the particular soil. If it's highly organic or has a lot of reduced minerals, it may have a much higher oxidant demand than you expect. Persulfate has a distinct chemical fingerprint. I'll show you the structure of it and gets a little bit more detailed, but we can get into analysis of active persulfates in groundwater, increases in the persulfate breakdown products. If you're using sodium persulfate, of course, you'd have sodium and then ultimately sulfate, potassium with potassium persulfate. And then, of course, what's your electrical conductivity, ORP, pH? These things vary over time. And then that analysis in combination with looking at what you know about your site can help you understand a lot more about your site itself. So this is a persulfate molecule. When I show this molecule, I like to say that, because it reminds people of how the chemistry works. At our plant in Tonawanda, New York, we take train cars full of sulfuric acid and hydrogen peroxide and enough electricity for 8,000 homes, and we put them together, and we make a shelf-stable persulfate salt that you can then activate and break down at your site to destroy your contaminants. And that, I think there's a pointer in here. Well, I guess I'll do it here. The oxygen-oxygen bond is what makes it a peroxygen or a persulfate. It's a very unstable bond in general. So that's where the energy is stored. So if you've got persulfate in groundwater, it ultimately breaks down to either the sodium or potassium cation plus the sulfate, and then you have ORP, pH, and conductivity, which I'll talk a little bit about. So what do geochemical data help you to see? Well, obviously you can see where did my reagent go? What's my radius of influence? You can get a sense of longevity. How was it transported? What's the residence time? Did it just move along or is it still in the same place? what's the potential for continued treatment? And I'll have a slide, just one slide on this, via anaerobic oxidation. We'll talk about that a little bit later. And then groundwater velocity and flow paths. And of course, you're obviously trying to target your source areas, so you take a look at what happens in all of these zones. So direct analysis, there's ways to do it in the lab. We have some field test kits that we make at our lab in Tonawanda, so you can look at distribution or ROI directly with these. It measures the presence or absence of persulfate over time. Typically, once the persulfate is dissolved and active, it only lasts about 2 to 8 weeks, so that's sort of the time frame, like say with sodium persulfate when it's completely dissolved, that you would be looking at. The test kits work in a range of like 1 gram to 100 grams per liter, so that's sort of a typical range that you would be working for remediation. I'll touch on that a little bit more later. You can also use these to look at persulfate in soil, although that's a little trickier because persulfate's really soluble, so you basically have to wash the soil to get it out to use a water test kit, so it's a little bit tricky. I've seen it done. Works best with a field lab where they have a centrifuge rather than muddy water, but you know. Show our molecules again here. Sodium persulfate, it's highly soluble, it injects as a liquid. By highly soluble, I mean like 500 grams per liter, so much like table salt. Potassium persulfate is a fraction of that, like 10%, so like 50 grams per liter, so much, much less soluble. They both release the persulfate anion, of course, and then either sodium or potassium. And then when we start getting into the geochemistry, of course, we need to understand what are the ratios of sodium or potassium to sulfate, and that gets into the molecular properties. So sodium has a lower molecular weight than potassium, so sodium persulfate or closure SP is about 19 weight% sodium, and closure KP, potassium persulfate, is about 29 weight% potassium. So when you get into looking at the geochemistry, you need to know those things. So obviously, if we're looking at closure SP, we'd look at analyzing for sodium and persulfate. KP, we would look for potassium and persulfate. Sodium and potassium are typically conservative. They typically move with groundwater flow. They tend not to be impeded or partition all that much. Sulfate can transform. It precipitates to form minerals sometimes, like we have seen in many cases where you have high calcium, you can have calcium sulfate, gypsum forming, and under reducing conditions, like that gets into the anaerobic oxidation realm. If you inject persulfate where there are hydrocarbons and over time the ORP drops, you can drop into the range where sulfate can be reduced to sulfide, and so that all of a sudden your sulfate concentrations can change. Also, off to the right, and I didn't try and overly complicate this presentation, you're often using an activator with persulfate, most generally, and the most common are alkaline activators. So typically with sodium persulfate, because it's soluble, you would use caustic soda. Well, that's going to have a sodium contribution as well. And most typically with potassium persulfate, you would use hydrated lime or calcium hydroxide. That's adding a calcium component. So you can look at those in your geochemical profile as well. These are the same ratios, but expressed in a way that you can understand. If you're targeting 20 grams per liter, for instance, in a groundwater pore volume, what do you expect to see in your wells? 3.8 grams per liter of sodium or 3,800 milligrams. Potassium, you would see a bit more because of the mass ratios. And the sulfate, you can almost read that as persulfate as well, because remember, the persulfate's 2 sulfate molecules together. So your persulfate concentration at its peak would be 16.2 grams per liter, and then when it breaks down to sulfate, that would be the same mass. It's not moles per liter, it's mass per liter. And anyway, you look at those concentrations and directly compare them to your injected dose. Am I getting the concentration that I expected, or am I getting something more? It's like, if it's less than expected, maybe your distribution wasn't the same that you had, or it moved outside of the zone. If it's greater than expected, maybe you've got some preferential flow to your monitoring point. It's all these kinds of things that you can look at. In terms of the key parameters to look at, the graphs are off to the right. They're way too tiny for the screen, and I don't actually have an electric conductivity graph there, which you would think I might have. The top one on the right is persulfate concentration. Then in the middle we have ORP, and then at the bottom we have pH. And so this is some work that Western Michigan University, Dan Cassidy, did some time ago. He was looking at our Closure CR, which is an alkaline activated form of persulfate. And so persulfate concentrations as they decline, I had mentioned 2 to 8 weeks. You can see that sort of applies to what he was doing, because he was directly measuring persulfate in the lab. It declines fairly quickly. The ORP declines in the second graph as the persulfate does, because we're getting away from that ISCO, that strong ISCO environment. And then the pH, this is, he was actually treating like PAHs in equilibrium with sediment. So the pH is somewhat buffered to the soil, but you can also see that the pH in this case returns to a near neutral of around 8. Now the reason it's higher at the start is that Closure CR that I mentioned is an alkaline activator, so it is we're typically targeting a pH of like 10.5 to 12 when we're trying to do alkaline activation. And of course the goal is to try and get that pH to return to near normal, because most people don't want to site at that pH. So what we like to see in the direct zone of influence, like we're doing some injections, what are we trying to get to? Well, we'd like to obviously get some good distribution. Greater than or equal to 50% of the pore volume. If we can get our target concentration of persulfate in there, we're doing pretty good, because we're able to treat that volume in that 2 to 8 week period. Conductivity, we'd expect to go up 2 to 3 orders of magnitude. It should jump up quite substantially. ORP plus 300 to plus 600 millivolts, pretty substantially much higher than you would see in a natural groundwater. If you're doing alkaline activation, which again is the most common, you'd expect your pH to be 10.5 or more during the time that you're doing your activation. Sodium and potassium and sulfate, proportional as I've talked about before. I've got a little bullet down to the right there, just to give you a sense of target persulfate pore volume concentrations. It really ties to the contaminants. So say for petroleum hydrocarbons, it ties into the specific pathways that we're trying to activate within ISCO. We only need oxidative pathways for petroleum because they're highly reduced compounds. Whereas if we have oxidized contaminants, chloroethanes, carbon tetrachloride, which is the reason that we substituted them for like things like turpentine, because they were not flammable. So those highly oxidized contaminants require what's called a reductive pathway. Rather confusing chemistry, but we need a higher concentration, and we need to use something like alkaline activation to ensure we get there, just so you have a sense. The timing of the geochemical footprint, I actually take this from right to left, because I think when I've tried to give this presentation to myself and I take it from left to right, I get confused. But if you get further down gradient or further along in time, you get to where you don't see the chemical footprint anymore. After a long time and groundwater has flowed through, for instance, your electrical conductivity, sodium, potassium have basically returned to background. There's a further up gradient point where ultimately you see no active persulfate. It probably doesn't reach it. This is like that 2 to 8 week post time frame sort of thing. If you're more than 2 to 8 weeks out, you probably don't see any persulfate. And then over time, your geochemical signature shows up and wanes. In the indirect zone of influence, so this is outside of where you directly inject, you'll see delayed increases in persulfate and your electrolytic conductivity and your sodium potassium, because it's not there at the time of injection. And of course, within your direct injection zone, immediate increases in these parameters. And so just to give you a sense of how you would look at it from a time perspective. Now, rebound versus recontamination. Obviously, it's really important if you do a pilot test, and your contaminant concentrations, you go back to monitor 3 months later, and your contaminant concentrations are the same as they were before you did the injections. Well, what does that mean? Well, you can't just say that it didn't work, because you got to look at the geochemistry as well. Do you have true rebound where the contaminants have actually repartitioned out of the soil organic matter or the fine soil particles and redissolved? Or do you have recontamination where contamination migrated back into that space? And that's where geochemistry can really help you to look at it. The real difference is, what do you see with those other parameters? The conductivity, the sodium, potassium, the pH. If those parameters remain relatively the same and your contaminant concentrations come back up, that's rebound, because your groundwater hasn't moved. You don't have fresh groundwater coming in. That's redesorption within that matrix. And then if you have recontamination from inflowing groundwater, maybe your sodium and potassium, look, they're not, those thousands of milligrams per liter. They're much more like your background. You're like, well, okay, this is flowing into my target area. So that's a very different interpretation of the result. So rebound, we typically think of an insufficient dose, although I will say that, because I dose a lot of these sites, most of our clients, of course, are consultants who are like, what do you guys recommend? And if you have a really high concentration hydrocarbon site, I might say, well, geez, in order to get enough mass into the ground to do what you say you need to do, to safely apply persulfate within the guidance that we would provide, you might need to do 3 rounds of application. So the rebound might be predictable. You might say, well, we actually needed to do this much, and it's not a surprise. We've probably taken that mass down by 1/3. Or did you have a lot more sorbed mass than you thought, or more non-target demand? And that's where it gets to be like really critical, that did you do a soil oxidant demand test ahead of time? Because we'll assume an average SOD of 1 usually, but it can vary a lot, and it changes the economics considerably. So you got to look at that. You may need to adjust the dose in those cases. Are there distribution issues? You may need to look at application method, maybe injecting on a tighter grid or something like that. For recontamination, you probably have